possible to give a talk. So already this week we've heard quite a number of talks that involved some large deviations somewhere in the talk, and so I will be mainly talking about large deviations today, and in particular for trajectories of Feller processes. And before I go to the problems that I really want to look at, I want to give two examples that kind of introduce the problem. So the first one is Schilders' theorem, which is kind of a theorem which takes the following. So you have independent copies of just a standard Brownian motion. And then you know by Kramer's theorem that at every time t you have a large deviation principle. But Schilders' theorem kind of does the following. It takes all times at the same time and proves the large deviation principle for that. So I've written the following. So for a continuous trajectory omega, we know that the probability that this trajectory, the trajectory of averages, that this is close to omega, decays, as we've seen before, as e to the power minus n times I of omega, where I of omega is the following rate function. So we look at the derivative of omega, and we square it, we integrate and divide by 2. And of course this we can only do if omega is absolutely continuous, and otherwise the rate function is infinite. In other talks already there was some talk about the Dawson and Gaertner theorem, which did something slightly more elaborate. So instead of looking at the averages of the Brownian motion, you actually look at the averages of the Dirac of the Brownian motion. So that's the following slide, the Dawson and Gaertner theorem. So it's exactly the same setting. We again take independent copies of Brownian motion. But now we take the average of the Dirac measure evaluated in the Brownian motion. And then we can ask ourselves the question, if we are close to trajectory mu, how does this probability decay? And here mu is an element in the Skålkot space where at every time you take a measure. And so the Skålkot space is a space of paths that have left limits and are right continuous. So again here we have the rate function, and it's actually of a similar form. So the rate function evaluated at mu is again 1/2 times the integral, and now we don't have the derivative squared, but we have some we have a more difficult object. So we have this norm here of the derivative of mu t in some sense minus the adjoint of the generator of Brownian motion evaluated in mu t. So as I said, so the generator is 1/2 times the Laplacian, and this norm that I've given here is actually the h-1 norm of mu t, which can also be given in the following way. So we take q, and if we evaluate q on f as the derivative of f squared, and then we take this kind of Legendre transform object. Am I missing one square? Here you mean. Yes. Okay. So this is a well-known result, and it's already from the 80s. But now you might ask yourself the question, suppose that I look at different processes, and my main motivation here is discrete interacting particle systems, as Johannes looked at also. And the question then is, can we also prove such a theorem? And then very soon you run into trouble, because the methods with which this theorem was proven involve many Hilbert space methods. And for that you really use the specific, the Dirichlet form here. And for these discrete particle systems, but also for already a drum process, such an approach cannot work. So we have to think of something else. So that's kind of the goal of the talk that I want to give. So again, for every time t, we know by Sanoff's theorem, by the law of large numbers actually, that the average for an arbitrary Feller process converges to mu t, when mu t is the law of one of the copies. And by Sanoff's theorem, we have a corresponding large deviation result for this at time t. So the goal is, as in the previous slides, to give a large deviation result for the whole trajectory. So at all times t together. Okay. So I want to set up some notation. So for a time homogeneous Feller process xt on a compact space, so now I'll restrict my attention to a compact space, I denote with st of f the semigroup of conditional expectations. Well, this is a map from the continuous functions to the continuous functions, and the semigroup is strongly continuous. So for every function f, we know that trajectory t mapping to st of f is continuous in the supremum norm, and also every map st itself is continuous. So this kind of brings us in the domain of semigroup theory, and there are many results known. So for example, we know that there exists a generator. So this is a well-known object, so it's simply defined by the time derivative at 0 of st f minus f divided by t. And of course this limit only exists in its domain. Okay, so now I want to turn to large deviations. And before I want to look at large deviations for the whole trajectory, let's first start with 2 times. So if we can do 2 times, then we can do 3, 4, and then use the Dawson and Gaertner projective limit theorem to get something for the whole trajectory space. So we start with 2 time large deviations. Okay, so I asked the probability that the averages at time 0 are close to a measure mu 0, and that the averages at time t are close to a measure mu t. And then you can show that this probability decays as the exponential of minus n times the entropy of mu naught with respect to the measure with the law of x naught. But there is an additional term, which is kind of the conditional rate function, which is given by the following formula. So it of mu t given mu naught is given by the Legendre transform of vt of f paired with mu 0. Well, what is this vt of f? It's kind of the logarithm of the semigroup st evaluated at ef. So this might be a strange expression at first, but if you think about it, normally if you look at Sanoff's theorem, what you will get as the rate function is the Legendre transform of the logarithm of the Laplace transform. So what is happening here is, well, I simply have the rate function for the time 0 marginal, and then I go conditionally on that result. I calculate that rate function. So what I do is not the Laplace transform of the expectation of e to the power f, but I take the Laplace transform of the logarithm of the conditional expectation of e to the power f. So it's really what you would expect. Something to note here is that this vt of f itself is also a semigroup, because it's a very small calculation actually. If I apply it twice, what is happening is simply that I take the logarithm of st e to the power logarithm sr e to the power f. Of course the e cancels the logarithm, and then s is a semigroup, so I simply get that this is so also this v is a semigroup. Well, then the claim is to understand kind of the large deviations of this 2 marginal thing, and hence the large deviations of the whole trajectory. What I really want to do is to understand this nonlinear semigroup v. So this kind of captures all the large deviation information that we want to look at. Well, then we can ask ourselves the question, for a linear semigroup, a lot of the information is present in the generator. So maybe we can also look at the generator of this nonlinear semigroup. So what is it? So what I want to do, I want to calculate again the derivative in time at t is 0. Well, essentially I use the chain rule because I have the logarithm. So if I calculate this, I will get the following quotient simply by the chain rule. And I use time t is 0, and I get the following expression. So I get the generator of the linear semigroup. Then I plug in e to the power f, and I multiply by e to the power minus f. So that's the generator of this nonlinear semigroup. And so we're going to use this semigroup to kind of study the large deviations. And something which I already want to mention, and which is not maybe also not so very strange, you see here that the conditional large deviations are kind of given by the Legendre transform of the semigroup. So also the Legendre transform of H should have some important role. Okay. Now there are two issues that I want to look at before I come to the main condition of the talk. And the first one is to see what we actually expect as large deviations. So what kind of deviations are typical to be seen. And so the first thing I want to look at is kind of the Gersanoff transform in this general setup. So suppose that I take a function g such that I know that e to the power g is in the domain of A, as in g is in the domain of H. Then I can look at the following quantity. So I take the exponential of g evaluated at time t minus g evaluated at time 0, and the integral from 0 to t evaluated in h of g. Wow. So I said before, this is actually a generalized form of Gersanoff's theorem. If you consider this as a function of t, this is actually a martingale, and it's a mean one martingale. Also, it's multiplicative. So you expect if you use this as the Radon-Nikodym derivative to define a new measure, you expect this Q also to be a Markov process. Okay. So we will look at this measure Q that has been defined by changing the measure P by this term. Well, it was proven in 2002 by Palmowski and Mowolski that this measure Q actually corresponds to a Markov process as well. Now, of course, if we look at diffusions, this is well known. But this is actually true in general, so we don't need any of the structure there. So I can define the following operator, which I call AG. And I define it in the following way. Well, it's actually quite a nasty formula, but if you actually start working with it, you will see very clear what will happen. And so I'll give two examples to see what you can actually expect with such an operator. So first I start with the Markov jump process. So a Markov jump process has a linear generator A, which is of the following form. So I take the sum over all sides y where I can jump to, then I have a rate r x comma y, and then I evaluate the difference of the function. If I then look at a to the power g of ag of f, what I actually see is that it has exactly the same form, except for that the rate has been changed by this exponential factor. So this martingale really changes the process in such a way that it still remains of the same structure, but kind of the jump rate is tilted. Well, for completeness, I have added also the nonlinear generator, which has a structure which is in a sense similar. So we put in the exponent the difference of the functions, and then we do -1. Yes?
Can we see this as a more general version of
Yes. Okay, and so the second example that I want to look at is the case that I started out with, so simple Brownian motion. So I have a generator which is given by 1/2 times the second derivative, and then if we start to look at these tilted generators, we see that a to the ag adds this drift term. And the nonlinear generator h is the original generator plus this quadratic form. So you really see that the structure of these generators is much different in the case where you work with a diffusion process, where you get this bilinear form, which very much aids the approach via Hilbert spaces. And this different situation where you get an exponential tilting, which of course is nonlinear and this cannot be treated in that way. Okay. Then I want to go to a problem, which is, so in the second slide, I looked at large deviations for these Brownian motions, and there I had absolute continuity for the trajectories of measures. Well, in that setting, we kind of know what to do with that and what that means. But in a completely general setting, it's kind of unclear how we should define absolute continuity for a trajectory of measures. And because I don't want to use too much of the underlying, in a general setting, I do not know much about my spaces. So I kind of want to come up with a definition of absolute continuity that kind of depends on my process. So I have this generator A, and I want to use this generator A to cook up a definition of absolute continuity. So that's what I want to look at. Okay, but first, some things that are important in this setting. Well, the space of Radon measures on my space E is, of course, the continuous dual of the space of continuous functions. And I denote, as before, f, mu, the dual pair between these two. Okay. I denote with mu t the law of xt, and then I have the following equalities. So if I pair f with mu t, then that's of course the same as calculating the expectation of f in xt, and then I can use the semigroup, which again I can write as st of f, mu 0, and then I take the adjoint of s, and I end up with f, st star mu naught. So apparently mu t is st star mu naught. Something which is also important is that the semigroup is strongly continuous. So what this tells me is actually that this trajectory, mu t, is a weakly continuous trajectory of measures. Well, this is very important because I want to come up with a definition for differentiability. And now I've seen that I have that I know that this trajectory is weakly continuous. So maybe I can also use such an approach to define differentiability. So okay, so I want to find a concept of how to differentiate such a trajectory. Okay. Now let's take a function in the domain of my generator, and let's see what happens. So if I try to differentiate, well, by what we saw on the slide before, I actually add st here, and if I differentiate that, I get an A, because this is differentiating the trajectory of the semigroup. So now if I proceed, I put the st on the other side again, so I get af paired with mu t. And because actually I want to have the function f free, I want to put a on the other side. But in general, A is an unbounded operator. So what I want to do is I want to take the adjoint of an unbounded operator, which is an operation I would rather not do, because the domain of the adjoint of this operator is very often not the whole space. So I only have this definition for kind of a subset of the space of measures, and hence a subset of the space of probability measures. But of course I want to be able to do this for any trajectory that I start with. So apparently I have to do something here. Also, I have this for all functions in my domain of A. But for many processes, it's actually very unclear what the whole domain is. So for diffusion processes, sometimes you can actually give the whole domain. But for discrete interacting particle systems, for example, it's unclear what this domain is. And you can only give a smaller subset, which then in turn is enough to determine everything you want to know. So that's the concept that I want to look at. So I say that the linear subspace of the domain is called the core for A if it's dense in a domain for the graph norm. So the graph norm of f is given by f plus the norm of the A of f. Okay. Well, sometimes it's kind of easy to find such a core. So let's give this lemma. A linear subspace that is dense and that is also invariant under the semigroup, that's always a core. So that's kind of an easy way to find one. Well, I kind of gave these two problems. So on one hand, I know that I have these transforms, and I kind of know that I get tilted Markov processes, so this will turn off. And I have absolute continuity of my trajectories that I want to be able to do. And so for that, I'll give a large condition in which I can state my theorem. And it's quite a long one, but it's the following. So to do what we want to do, we need a core. We need to have a core for A. And on this core, we want to have a topology. And I'll call it tau D. And, well, D with tau D needs to satisfy some properties to do everything I want. So recall that I had these changed generators AG, which were defined, maybe I should write it down. So I had AG of F was given by e to the power minus G, A, like this. So the first thing I want to be able to do is to actually write this down. I need to be able to do this on my core D. So if I want to be able to evaluate A in e to the power G times F, I need to make sure that e to the power G, let's say if G is in my domain, I want e to the power G to be in my domain, and if I multiply it with a function F in my domain, I also want this to be in a domain. So that's kind of the first property. Well, the second property is that I want D with this topology to be a separable, barreled, locally convex Hausdorff space. Well, that's a long line, but essentially this is satisfied, for example, if my space is a separable Banach space. And what this kind of will imply is that the space is reasonable as a space to work with. So don't worry about that too much. The third property is that this topology tau D is actually finer than the subnorm topology restricted to D. Now, what will that imply? That will imply that actually the space of Radon measures on E is actually a subset of the adjoint of D. So if I have a probability measure, it's actually also an element in D star. Okay, so the fourth property is one that I need, but which I think can be weakened. So I won't pay much attention to that. Well, the fifth property kind of boils down to the two problems we have looked at. So recall that I wanted to be able to write down a nice definition for this. And now that I assume that my operator A is actually a continuous operator from D to the continuous functions, I know that I can take the adjoint. So this element here now, which previously I didn't know how to do because I was taking the adjoint of an unbounded operator, now becomes the adjoint of a nice and continuous operator. So this thing actually becomes an element in D star. And similarly, I can do this for all my processes that I get by the Girzanov transform. So also for that, this is satisfied. Well, the final one is a property on, let's say, the growth of H, and this will come in handy later. But the first thing I want to look at now is how now to actually differentiate a path of measures in a suitable sense. So I now can define D star absolutely continuous trajectories. So that is what I was after, and this is what I will need for my setup. So I'll say that the path of measures is D star absolutely continuous if there exists a measurable trajectory in D star for the weak star topology on D star, such that for every f in D, I have that this integral is finite. And most importantly, if I differentiate this difference, where here I have these probability measures, I actually get as a result this element in D star. So this gives me, so this must hold for almost every t. And then of course it's justified to say that ut is actually the derivative of ut. So that's the setup. Okay. So of course what we then also have is that if we look at the difference of f comma mu t and f comma mu 0, that we can actually express this again as an integral. An integral over the pairing f comma mu dot s ds. And we can also pull the integral inside, and for that we need to be able to integrate in d star, and for that we need all these strange properties of d, which is technically necessary, but okay. Well, now we come back to the thing we started out with. So v was the Legendre transform of let's say the conditional large deviation rate function. And so I want also to have the Legendre transform of h. And this we will call the Lagrangian, which I can now define. So the Lagrangian becomes a function on the probability measures times d star. So where the first index is to be interpreted as a position, and where the second index is to be interpreted as a speed. And this is simply what you would expect. So I pair f with the speed u, and I subtract hf comma nu. Well, as a consequence, we get that L is non-negative, because if we plug in the zero function, all the things I've written down are zero. It's lower semi-continuous, because all the pairings that I've done now are continuous. Lower semi-continuous with respect to the weak and the weak star topologies. Of this L now, we can, this L has some very nice properties under the conditions that we started out with. So this is already a good start. But what we also have is that the level sets of this L are compact in PE times D star for the weak and the weak star topology. Secondly, we know much more. So suppose that I give a positive n and some fixed time t. If I look at all trajectories that are absolutely continuous up to time t, that have Lagrangian cost bounded by m, then this set is actually a compact set in the space of continuous trajectories on PE, or also in the Schorkel space on PE. Okay. So these are two properties that we really want to have. Let's give a short proof of the first one. Okay. So recall this this condition completely at the bottom in terms of the growth of h. So there was a symmetric neighbourhood of 0 in D, such that if I take the supremum over all functions in that neighbourhood of h of f, this was bounded above by 1. So suppose that this neighbourhood exists. Then I give the Bourbaki-Alaoglu theorem, which is kind of an extension of the Banach-Alaoglu theorem, which you, I guess, know. If you look at the dual ball of a Banach space, then you know that this dual ball is weak star compact. Now this theorem has a generalization in the theory of locally convex spaces. So I replace my my norm ball, I replace it by an arbitrary neighbourhood of 0. If I then take the polar, which is the following object, so I take the polar of this neighbourhood, which is defined by all the elements u in D star, such that the pairing of f with u is bounded above by 1 for all f in this neighbourhood. So if you would have a Banach space and you would take n to be the unit ball in the norm, then this is exactly the dual ball. And the Bourbaki-Alaoglu theorem says, well, also in this case, we get a weak star compact set. So how does this help us? Now, take a function f in n, and take a u in this set. So actually I need to take a pair, a measure mu and u in this set. but the space of polar T measures was already compact because E was compact, so I only need to show that, that the speed is in a compact set. So let's look at the pairing f comma u. Well, simply by the fact that L is the Legendre transform of H, I know that f comma mu without the absolute values is bounded above by hf comma mu plus the Lagrangian. Now, of course, I can do the same with a minus, and then I'll get H evaluated in minus. Okay, so now I use the two properties that I have. The first of them is that f was an n, so I know, yeah, and n was also symmetric, so also minus f is an n. So I know that the first term is bounded above by 1, and I assumed that L was bounded by C. So I know that this pairing is bounded above by 1 plus C. So this kind of tells me that U is actually in 1 plus C times this weak star compact set. Now, of course, if I scale a weak star compact set, it remains weak star compact. So this tells me indeed that the level sets of L are compact. So that's a very useful result, and which we really want to have, because if we don't have compactness of these level sets, then we cannot really work with this Lagrangian. So this is an important result. Okay, so let's proceed. We can now kind of give a new expression for the semigroup, which of course involves this Lagrangian. So under the main condition, we can write the following. So I had the semigroup Vt of f evaluated in mu. Now I can give it this variational expression. So I look at all absolutely continuous trajectories nu that start in mu, and I pair f with where m at time t, and I subtract the Lagrangian cost. Now, why are these two the same? I won't go really into the details, but essentially the main, how you can see it is kind of, if you again try to differentiate this object, or let's say this object here on the right, and you don't mind too much about the details, so suppose that I can kind of differentiate inside without regarding the supremum. So if I differentiate on the inside, then I know, because this is an absolutely continuous trajectory, that I get f paired with nu dot at time 0. Now, if I differentiate the integral, I will get exactly the Lagrangian of nu 0 comma nu dot 0. Now, of course, nu 0 was mu, so that explains this mu here. And so what remains, let's say outside, is still the supremum over all trajectories that started in mu. But because only, let's say, the initial speed is left, this supremum actually reduces to a supremum over all initial directions to start in. So this supremum becomes this simple one. And so what I'm left with is simply the Legendre transform of L. But L was the Legendre transform of H, and even though I didn't state it, H is convex in F. So this again becomes H of F. So we kind of see that both semigroups have the same generator. So that in turn implies that they must be the same. So we have this equality here. So now how can we use this to go to the large deviation principle again? So as a result, if I look at this conditional large deviation rate function, I know that it is given by the supremum, let's say the Legendre transform of V. But now I have this variational expression for V, so I can just simply plug it in. So I have the supremum of all functions, and then I get minus the supremum over this difference, so that becomes the infimum. So I get the supremum over the infimum over all trajectories of f comma mu t minus f comma nu t plus the Lagrangian, the integral of the Lagrangian. Now suppose that I have some kind of minimax lemma that I can use, and that I can interchange the supremum and the infimum. So what would happen if that would be satisfied? So I won't prove that you can do this, but believe me that you can do this. But what happens if I would do that? So then I put f on the inside, and well, for any trajectory, the integral of the Lagrangian doesn't change. So so the only part that is kind of variable, if I have to choose f, is this starting point. Now, if mu t and nu t are not the same, I can of course, well, f is still variable, so I can blow up this difference. So this will give me an infinity. But then I want to take the infimum. So all the trajectories that kind of give this infimum, give infinity, will not be picked by my infimum. So I can just throw these out. So this would mean that I actually have to take the infimum over all trajectories that start in mu naught and end in mu t. And so that's what we have here. So what remains is this infimum, starting in mu naught and ending in mu t. And then, of course, the Lagrangian is still left. So this kind of means that this conditional rate function that we have here can be expressed as this infimum as an integral over this Lagrangian, which is, of course, what we were after. Yes? Yeah, so this is the argument that, so suppose we're able to change them around. Well, then, of course, we have a fixed trajectory, and then we start to take the supremum over f. Because we have a fixed trajectory, this Lagrangian part doesn't change. So what is left is the difference of these two pairings. But we still have to take the supremum over f. So if these two measures are not the same, then of course we can, we can pick f such that this difference becomes very big. And then, of course, we can pick it as big as we want. So then the supremum would blow up. But then we have to take an infimum over all trajectories. So all these things, they are not going to be picked. So we can throw them out. Yeah. Okay, so, well, that's kind of what we were after. So we wanted to understand this two-time conditional large deviation rate function. And it's now expressed as the integral over Lagrangian, and then an infimum over all trajectories. And then, essentially, it boils down to the use of the Dawson-Gärtner projective limit theorem, which says that, well, if you can do this, if you can do the large deviations for 2 times, and for 3 times, and for 4 times, and for an arbitrary number of times, and you kind of have a nice rate function, I will not go completely into the details, you can actually pull it up to the product space, and then you have a large deviation principle there. And then to get it to this space, you would still need exponential tightness. But that's also a detail which I will not go into details here. But essentially, the finite dimensional problems give you the result in infinite dimensions for let's say, all times together. And the rate function then is given by the rate function for time 0 and this integral over the Lagrangian for an absolutely continuous trajectory mu and infinity otherwise. So this is kind of the result that we were after. And it's also the result that the Dawson and Gaertner theorem gives. But these methods do not refer to any of the structure that was present in that problem, and essentially is completely general. So that are the closing comments, relatively fast. So the theorem, so that's the first thing I want to mention. So I proved it for compact spaces. I've shown it for compact spaces here. But you can actually generalize this to locally compact spaces, because this boils down to one-point compactification, and you can argue via that. And partly generalizes the Dawson and Gaertner theorem. And this was kind of contained in the fact that in my conditions, I kind of needed that my semi-groups ST and VT were strongly continuous for the space D. And this would kind of imply that for the Dawson and Gaertner theorem, I can only prove it if, let's say, the drift and the diffusion matrix are sufficiently differentiable. Of course, the Dawson and Gaertner theorem is valid more general, so there is something to gain here. But still, it gives a general approach that at least goes in the right direction. What maybe should be said, the original thing I wanted to look at, for example, discrete interacting particle systems, as in that you can find in the book by Liggett, for that the theorem also holds. So indeed, it generalizes to processes that you actually want to look at. Okay. Well, a second thing maybe is that, well, it's often hard to get an explicit formula for L, but still, it's a Lagrangian, and you can use all the techniques kind of that are available in the literature. And so a question that I'm asking myself, is there some geometry to be discovered here? Because you start with some kind of strange space D star that you use as a tangent space. And the question is, well, can you actually work with this? Because it's quite of a different structure than the normal geometry that you would look at. Okay, so work that is in progress, and which is relevant for statistical physics, is for large deviations of the following kind of trajectory, the following trajectories. So suppose that I have a process on -1, 1 to the power z. For example, modeling a magnet. So at every side you have a magnetic spin, and you have some process that evolves that. Can you then also look at large deviations of this object? So I'm not taking independent copies now, but I'm taking shifts, and I take the average. So that's kind of doing large deviations for around the ergodic theorem. So in the problem that I looked at, we looked at the law of large numbers, and this would be around the ergodic theorem. So for that, we now have a large deviation principle for a big class of processes, but not necessarily for all processes already this Lagrangian form of the rate function. So that's work in progress. Okay, thank you very much. Yes.
Is there like cases that your work like satisfies but not satisfied
so in Jin-Fangs they go very much via so you have this operator H, and then you would kind of like to show that it actually generates the semigroup V. And for that he has many techniques, and well there if you know then that H generates a semigroup, then afterwards he uses kind of the same techniques to obtain this Lagrangian formulation. So in obtaining this Lagrangian formulation, it's very much similar work, where here of course what is new here is that you use this D star as a tangent space. But apart from that, it's similar to what was happening in that book. But for showing that the semigroups are the same, so the semigroup V and this variational semigroup, there I use a more direct approach, actually really showing that kind of the trajectories that you will see in a supremum, I really show which ones these are. And so I don't really need to use the methods that are in the book. So in that sense, it's different. Yeah.
But how about like exams? Like any exams that your method covers that?
Yes, I would say all the examples that are not the diffusion case that are not in his framework. Yeah. Well, essentially that's kind of what's in the back here. So normally you would have that convergence of linear semigroups gives you reconvergence, and convergence of nonlinear semigroups would give you large deviation principle. Yeah, but then how to put it? So essentially what you have there is, so you have nonlinear semigroups that need to converge. That would give you a large deviation principle. But okay. Okay. Mm-hmm. Yes. I have not looked at it, so but I certainly think that for more difficult processes, at least this approach with these new tangent spaces and stuff, yeah, you could have a look at it. Yes, but we can talk about that afterwards, I think. Yeah. Mm. Yeah, so what I said, it's only for a smaller class of processes. So these are, let's say, already at time 0, you need to start with a measure that's either Gibbs or something which they call asymptotically decoupled. So different regions in space cannot have two big interactions. And then also you would need a process that kind of preserves the property. So you cannot build correlations too fast. So it still needs to be of a kind of local nature, and the process shouldn't destroy this. So yes, there are quite some conditions, but for example, yeah, what I said. So this model of magnetic spins, and then if you have some dynamics that would heat the system up or cool it down, so these preserve this local nature, and so for that you can do this.